So I started studying complex analysis. I'm currently studying the complex differentiation, and I came up this question. It's complex valued complex variable function. First, we have to find whether this function satisfies the Cauchy Riemann equations. Then we have to find whether uh, the derivative of f is available at the origin, or rather the z equal 0. So first of all, there is a thing to note that we can write any complex variable function as a sum of two real variable functions. So this is a complex variable function. So on the right hand side we have two real valued real variables functions. So this we call as the real part of f, and this is the imaginary part of f. So uh, in order to transform uh, if z to this form, we need to replace z by x plus iy. So that's what we are gonna do. First of all, we have to replace z by uh, x and y. So we will get, by simplifying, this is just x minus iy squared, denominator is x plus iy, where the origin x y is not equal to the origin. Then we have here 0, where xy equals to the origin. So okay, now we have to simplify this one in order to get this form. We have to simplify this fraction, or this quotient, in order to get the function looks like this form. So it's just a simplification. So we just when we bracket out this term, and by the by multiplying both numerator and denominator by the conjugate of this one, which means x minus iy, we ended up getting x cubed minus 3xy squared, x squared plus y squared plus I, and we have here y cubed minus 3x squared y plus x squared plus y squared. Here xy is not equal to 0, 0. This is just a 0 otherwise. Okay, uh, this is just the simplification. First you have to bracket out the numerator, and then you have to multiply it by the conjugate of the denominator. When conjugate of denominator is x minus iy, when you multiply by x plus iy with x minus iy, you will get x squared plus y squared. Then you can separate the terms involving I and terms do not involve I. So likewise we can get this function into this form. So here now that we have found the form, it's worth to note down what our capital Yx, or rather the real part of this function, and the imaginary part of this function. So here my real part of this function is, again, it's a piecewise function because we have a 0 here. This one is the our real part of the function. So this is what I call uxy. So simply it is x cubed minus 3x y squared, x squared plus y squared. Okay, this is where the xy is not equal to 0, 0. Otherwise, it is 0. Okay, now, likewise, we can write our second real variables function, which means the terms involving y, which means this one. Here we get y cube minus 3x squared by x squared plus y squared, where again x and y not equal to 0, 0. Otherwise, it's a 0. Now that we have found the both real part of the function and the imaginary part of the function, now we have to evaluate the partial derivative of each of these real variables function. So in order to evaluate the partial derivative at 0, because we are trying to ensure that this function satisfy the Cauchy Riemann equations at z equals 0. So in order to find that, we have to evaluate the partial derivative of each of these functions at the origin. But we can't simply do that because this is a piecewise function and this is not defined at the origin. So therefore, we use the definition of the partial derivative in order to evaluate the partial derivative of these two functions. So first of all, what does the Cauchy Riemann equation says? Cauchy Riemann equation says partial derivative of u is equal to partial derivative of y and uy equal to minus va. These are the relations that comes from the Cauchy Riemann equation. If the function is differentiable at z equals 0, then this relation is satisfied. But the converse is not true. It's not sufficient to say that satisfying the Cauchy Riemann equations guarantees the differentiability. In fact, this is a counterexample for the converse of this theorem. Okay, okay. Let's find the partial derivative of this one. So partial derivative of u x is just the limit of h approaches to 0, where we are taking the partial derivative with respect to x. Therefore, the x coordinate in terms with h, then this is the definition of partial derivative. This is plus here. Okay, so now you just plug the values. Limit of h goes to 0. Here we have UH0. Here you have U0, 0. Then here h. Okay. Now according to our function u, just plug h instead of x, then 0 instead of y. In this function, you plug h to the x and 0 to the y. So we will end up having this term h cube over h squared. U0, 0 is 0 because this is defined. This function is defined at the origin as 0. Therefore, this is 0. Then you have h here. So simply you get 1. Okay, so ux you get 1. Now uy, similarly you evaluate by using the definition of the partial derivatives. You evaluate this one, then limit again h goes to 0. Sorry. Now h term is goes with y because we are evaluating the partial derivative of u with respect to y. Therefore, this is where the h comes to play. u00 again. Likewise, you can have the answer as 0. Just plug these values to the original equation and you will ended up having 0 as the answer. Likewise, you will evaluate vx and vy too. So by using the definition, when you evaluate vx at 0, 0, you will have 0 and y as 1. So by using these four answers, we can form the relation where ux equal vy and again uy equal minus vx. So this is the relation of Cauchy Riemann equation. So at z equals 0, at z is equal 0, Cauchy Riemann equations are satisfied. So at z equals 0, Cauchy Riemann equations are satisfied. So okay, so is this enough to say that the function is differentiable at the origin? So now we know that the Cauchy Riemann equations are satisfied at the origin, but is it enough to say that the function is differentiable at z equals 0? So our theorem is that if f is differentiable at z naught, some point z naught, then Cauchy Riemann equations are satisfied at z equals 0. But here we arrive the converse of this statement, whether the converse is true. If the Cauchy Riemann equations are satisfied at z equals 0, can we say that the function is differentiable at that point? So that's the converse of this statement. Actually, no. In fact, this example is a counterexample for that statement, the converse of this theorem. So shall we evaluate the the derivative at 0 by the definition? It's just the limit h goes to 0 where f0 plus h minus f0 over h. Here you get by substituting into the function, you get h bar over h. This is just a 0, so minus 0 does nothing to our equation. So it's just limit of h bar over h square where h goes to 0. So if this limit exists, we can say the function is differentiable at z equals 0. So now we have to find that whether this limit exists or not. In order to do that, since we are in the realm of complex numbers, unlike the real numbers, there are so many ways to approach 0 in the complex plane. For example, I will compare it with the real case because this is a real number line. Say we have to find the limit of some function when x arrives to 0. There is only two ways. There's only two ways to arrive at 0, on the right and on the left. If we calculate the limits from the both side and then they are turned out to be equal, we say the limit exists. That's with the real case. But in the complex plane, there are so many ways to approach 0. You can come along the you can come along the real axis, as in the real case, and also you can come along the imaginary axis by both sides. Not only that, you can come along these sides too, and also these sides. So there are infinitely many ways to approach the limit at a point in the complex plane. Therefore, it is practically impossible to calculate all the limits. So if all those limits are equal, we say the limit is exist. Limit exists. If all the paths leads to the same value by taking the limit, we say the limit exists, but it is practically impossible to calculate these all values. Therefore, that's why we have theorems. But if we come up with different paths which lead to different answers, for example, say you get some answer along the x-axis, sorry, real axis, but you get another answer from the imaginary axis. Therefore, since those two answers are not equal, we can definitely say the limit does not exist. So that's the strategy we are going to apply here. First, let's send h equals 0 along the real axis. Before that, takes h as h1 plus I h2. Here h1 lies in the real axis and h2 lies in the imaginary axis. Okay, so if we are to send h to 0 along the real axis, it's just this side, which means h2 is equal to 0, because now we are sending h equals 0, h to 0 along the real axis. Therefore, h is equal to h1. So simply you have this limit h1 approaches to 0. h2 is now 0. So conjugate of a real number is just the number itself, which definitely 1. So this is our 1 limit. Okay. Now, if you try to send this limit along the imaginary axis, you will ended up having again 1. So that's not helping. So instead, send h approach to 0 along the h1 equals h2 axis. Okay, so we have h equal h1 plus, now h2 is also h1, so h1 can be taken out, h1 plus I. So now plug these values to the h approaches to 0 limit. So first the conjugate of this one is 1 minus I, then h squared means h1 squared 1 plus I squared. So these terms are cancels out. This is a constant and not definitely equals to 1. This can't be equal to 1. Okay, so because this is some number, because there are no any h terms involved here, therefore limit itself is this number and it's not going to be equal to 1. Therefore these two limits are not equal. Therefore the original limit is this limit does not exist. This limit does not exist means the derivative at z equals 0 does not exist. So, but previously we have found that at z equals 0, Cauchy Riemann equations are satisfied, but after checking out the definition of derivative, we have found that the derivative at that point does not exist. Therefore, the converse of this theorem is not true.